Step into the fascinating world of manga as we unveil the secrets of the majestic Stille bird from Frieren, beyond Journey's End. With its ability to soar faster than the speed of sound, it's no wonder it's the focus of a thrilling pursuit in the story. But could this imaginary creature exist in our world? Join us on a compelling journey as we bridge fiction with science, exploring the possibilities and limitations of Stille's supersonic flight. Don't miss out on this epic exploration into the realms of manga and science. At first glance, Stille presents itself as a creature of commonplace avian design. Yet, upon closer examination, it beckons a deep and captivating query. How does this apparently ordinary bird manage to execute supersonic flight with merely a single beat of its wing? Unlike ordinary bird flight, breaking the sound barrier is a feat beyond simple flapping. Pushing air backward creates thrust, but at supersonic speeds, air compression becomes a major hurdle. Stille's propulsion would be more akin to a miniature rocket than a bird. As for bird wing flapping, it's essentially pushing air backward. Inherently, bird wing flapping is quite efficient because the mass of the air being pushed back is counterbalanced by the mass of the air itself. Thus, one wing flap generates an effective thrust, allowing the bird to move forward rapidly with the tiniest force. However, when the speed we're talking about is the speed of sound, the air pushed back from faster-than-sound wing flapping would be compressed much more before it can transmit momentum back to the atmosphere behind it. This would make Stille's propulsion much more akin to a rocket than a regular bird flight. Calculations reveal that Stille would need to compress a significant amount of air with each flap to reach these incredible speeds. This compression requires immense force, pushing the limits of bone structure and material composition. Ordinary calcium bones wouldn't stand a chance. So, what could Stille's bones be made of? While we can't be certain, the answer likely lies in fictional materials beyond our current understanding. For this compression, after calculating the air volume, the bird's wings would compress in one flap. Along with the equation of the airspeed that must be pushed backward, let's assume Stille weighs 1 kilogram, has a wingspan of 1.2 meters, and a wing area of 0.044 square meters per side. By integrating the wing flap volume, the maximum volume of compressed air would be 77 liters. This air volume would be enough to propel a 1 kilogram Stille at a speed of 330 meters per second if it were propelled backward at a speed of 4,000 meters per second. If we consider an ideal energy conservation process, converting potential energy into pure kinetic energy, we'd need to compress the air from 1 to 80 bar. So Stille can be able to propel itself forward at nearly the speed of sound with just one wing flap. But the challenges don't stop there. Stille's feathers need to withstand the intense heat and friction generated by supersonic flight. Once again, science fiction takes the helm, indicating the need for feathers with properties far exceeding those of any known bird. Abandoning the limitations of traditional bird flight, a more feasible solution emerges. Imagine Stille utilizing a miniature jet engine. By compressing air and propelling it through a nozzle, Stille could achieve incredible speeds without relying just on wing power. Such a system would require a combination of factors, including internal fuel production, efficient energy transfer, and the ability to handle the compressed air. While this scenario might seem fantastical, it aligns with the laws of physics more closely than classic wing flapping at these speeds. Wait a minute, 4,000 meters per second correlates to Mach 12. An 80 bar of air would enter a supercritical fluid state. This indicates that the amount of compression and air propulsion isn't even taken into account yet. The incomplete energy conversion process loses energy in the form of heat from compression. The air is lost from fast wing flapping, and when the air expands, it absorbs heat, causing the volume to decrease again. But even so, it might still be possible. No physics law forbids birds from flying at the speed of sound, but the materials for Stille's feathers and bones likely won't be natural. As for the energy needed for this flight, at a minimum, it's the energy needed to propel itself forward and the air propelled backward. The minimum energy requirement is 748 kJ, with 100% energy efficiency. If we presume diesel fuel has an energy value of 38,000 kJ/kg, Then Stille, with a mass of 1 kilogram, would only use about 2% of its body mass to propel itself at a speed of 330 meters per second with a wing flap. The fuel indeed needs a combustion reaction, and does Stille have enough oxygen for that? Assessing the molecular structure of hydrocarbon fuel, 20 grams of hydrocarbon fuel will require about 3/2 moles of oxygen, or about 68.6 grams. The amount of oxygen that hemoglobin and blood combined in humans is only about 200 milliliters per liter, which equates to about 0.2 grams in weight. Even at maximum hemoglobin concentration, it's still far from the required yield of 68.6 grams. However, Stille likely has to compress the air into liquid form to send energy to the cells. But air is 79% nitrogen, so the compressed liquid air must be 327 grams. While Stille's existence breaches the limitations of real-world biology, it allows us to explore the mesmerizing possibility of theoretical scenarios. By pushing the limits of fantasy and science, we gain a deeper appreciation for the complexness of the natural world and the inventiveness of human creativity. This is just one example of how science fiction can spark curiosity and ignite our scientific spirit. What other fictional creatures could hold the key to scientific breakthroughs? Share your opinions in the comments below and explore the wonders of science, real and imagined, together. You can watch our recommended videos here.